So today we're going to be picking up where we left off with topic modeling, and then we'll move on to sort of our first discussion of variational inference. Variational inference is a particularly important topic, primarily because it offers us a very different way of going about approximate inference. And once we think about approximate inference in that way, it sort of opens up a lot of opportunities for us. And in particular, it will open up opportunities for us in the context of deep generative models, or these models that have become increasingly common in deep learning. And I think one of the interesting aspects of this course is sort of at the prior to the start of the semester, I'd had a conversation with Russ Selikutinov, who's teaching 10.417 and 6.17, which is the course that's running in parallel to this one, focused on deep learning. And we had this conversation about, is it appropriate to actually include deep generative models in this course, 4.18, 6.18? Because they're also going to talk about them in 4.17, 6.17, and we didn't want too much overlap. And as we got to talking about this, we realized that by including them here, we actually provide ourselves with a really unique opportunity, which is that we are going to get into that discussion after we've spent some thorough time deeply understanding variational inference. By contrast, your typical deep learning course doesn't have time, or doesn't make time to go into this topic. And so the typical presentation of these deep generative models that rely on variational methods sort of sweep a bunch of the details under the rug, which still offers a really sort of interesting high-level picture of what's going on, but we'll also be able to get more of the low-level picture of why those methods are actually working and what the mechanics are that are driving them. And so I think, in general, this is kind of a unique opportunity that we have as we kind of move forward from here. Okay, so we'll be wrapping up the structured SVM homework on November 6th, which is today, and then we'll be releasing homework 4, where you'll be applying Markov chain Monte Carlo methods in the context of a topic modeling problem. And there we'll be sort of pushing beyond the basic LDA model that we'll be talking about today to one that actually incorporates some Gaussian distributions in kind of a fun way. Okay, so before we wrap up LDA, I wanted to do a quick recap of the model itself, and then we'll pick back up with the actual discussion of inference. So we had said that latent Dirichlet allocation starts with this notion of a Dirichlet distribution over topics, and these are distributions over words, and they're shared across the entire corpus. And we could visualize a topic with its high probability words, and we could, sort of post hoc apply a label to those topics if we wanted to kind of interpret them. So the generative story for LDA then says that the way that we generate a document is by sampling a distribution over these topics, and then for each word we sample a topic assignment, so that's like a color for the word, and then we sample the actual word from the corresponding distribution. In this case, we sampled topic 4, which was green, and then we sampled the word maybe a pair of words here, Coast Guard from the distribution 5.4. So we can proceed through and generate entire documents in this way, and the crucial decomposition that we have here is this distribution over words and this distribution over topics. And we saw last time that these two modeling goals are kind of at odds with each other. And it's that tension between them that actually gives rise to something interesting. and that allows us to find groups of sort of tightly co-occurring words in interesting ways. Okay, so now we want to have this discussion of Bayesian inference for parameter estimation. And so to do that, we want to begin by thinking about what it would be like to learn this model if we were just treating it as a fully observed Bayesian network learning problem. Okay, so this is the problem that we solved many lectures ago, where we said that this just boils down to sort of count and divide. Right? All of these z's without the priors are really just going to come from some multinomial distributions parameterized by theta. And so for each document, we would just count up the number of times that each topic occurred. And for each document, that would give us a little vector of topic counts. And then we just normalize that vector of topic counts. Okay? And so that would allow us then to say that basically we get this decomposition, which is that the vector theta m is just the theta m that maximizes the probability, or rather the log probability of all of the word and topic assignments for the particular document M. Right. And so here we would just have log probability of z mn given all of the x's and the vector theta m. Okay. And then we would do something analogous for the actual topic vectors, where we would say we're just choosing the vector phi k that maximizes the total probability of all of the actual word topic pairs where the particular ZMN is assigned to some topic k that we care about. So we would have a sum from little m equals 1 up to capital M, a sum over all the words for that document. I guess here we have nm words in a document. And then we would say that we have some log probability of, I guess here we want the joint probability of ZMN and XMN. And here we would again have the joint probability of ZMN and XMN conditioned on theta m and phi k. And crucially here, we would only care about the terms in that summation for the cases where the particular z was actually equal to, so let's run out of space here, write this down here. So there would be this indicator that says, is ZMN equal to K? Okay. If it is, we'll include that term. If not, okay. So if we wanted to adapt that, oh yeah.
It wasn't clear to me about topic assignment is an observed variable, like observe, right first off.
So here, the whole, so this is crucial to this slide. At this moment, I'm saying, what if it were observed? Okay, in all the remaining slides in this section, it's not going to be observed. And in practice, it's not going to be observed. And in fact, it would be extremely strange if it were. But we want to make sure that from a graphical model's perspective, from a learning perspective, the actual problem that we would solve if it were observed is really easy. So that's the key takeaway. Not that this is in any way realistic. Okay. So similarly then, if we just added some priors of the parameters, this would just change that maximization a little bit. And this alpha and the beta would make their way into the sort of count and divide process, the same way that priors make their way into naive Bayes for map estimation. Okay, so now let's move to the realistic scenario. Okay, the realistic scenario is that you only observe x. You don't know what z is. So maximum likelihood estimation is finding the theta that maximizes the probability of x given theta. Map estimation is maximizing p of theta given x, which is proportional to p of x given theta times p of theta. And the Bayesian approach is to estimate this posterior, p of theta given x. Okay. So crucially here, for all of these cases, we have that this maximization problem is not exactly easy, right? Because what's really going on here is that we're summing over all of the unobserved latent variables z for the joint distribution p of x and z given theta. Okay. And so, in general, that marginalization might is sort of the source of one of the key challenges of this learning problem, because now we essentially have to solve two problems at once, right? We need to maximize over the parameters, but we also need to marginalize over the latent variables. Okay. So, and this also shows up in the estimate of the posterior, right? This posterior distribution is really a marginalization over the latent variables z. Okay. So even estimating the posterior requires solving this inference problem. Okay. So from your background survey, I think about half of you have seen expectation maximization in an intro ML course. So we're not, right now I'm not going to sort of belabor this point about EM, but I do want to kind of connect it back to EM, and we might actually talk about EM later in the course once we talk about variational EM. So if you know the EM algorithm, then one way of solving this unsupervised learning problem would be to solve an alternating optimization problem, moving back and forth between the parameters and the latent variable z. Okay. And so here, standard EM would go back and forth between choosing in the M step the values of theta and phi, which maximize over p of the expected value of these parameters, theta and phi, and z given x. And in an E step, estimating the estimating the actual distribution over the latent variables. So this back and forth between maximum likelihood and estimating latent variables is called the EM algorithm. And conceptually, you could actually think of this in a really simple way. So we're going to take this and we're going to generalize it to be EM with priors, right? And it would just be like before, but now we have Dirichlet priors over the parameters. And conceptually, it's actually really easy to think about how this algorithm works. If you just think about Monte Carlo EM. Okay. So Monte Carlo EM is an algorithm whereby we are essentially doing something almost like the EM algorithm, except that we're alternating between optimization and sampling. So suppose, for example, you just take one sample of the latent variables, right? Okay, so how would we take a sample of the latent variables from this model? If we already knew what the parameters were and what the x was? Yeah, so the E step here would say, for example, take one sample of z from P of z given the parameters and x. Okay. And then in the M step, and let's call that sample z hat. Okay. In the M step, choose theta and phi, which maximize the posterior of the posterior of theta, phi, given x and z hat. Okay. So to accomplish the E step here, right, what do we need to do? We need to run something like Gibbs sampling, right? Okay, and that would allow you to take one sample of these z variables. And how do we accomplish this M step? Choosing these parameters that maximize that posterior. So it's not really a sampling problem because we want the actual maximum, right? We want the values of those parameters that maximize the likelihood. No, it's even simpler than that. We actually just did it. What's that?
Take a map and
Yeah, it's just the map inference problem, right? If we know what x and z are, we're back here, right? Okay, so what is the one case where x and z might be observed, so to speak? Well, it's the M step of Monte Carlo again, right? You just sampled a value of the z's, and okay, they're not the real z's, they're just a sample of the z's. But you can treat them as observed and then optimize over the parameters. And the optimization problem, it would look just like this, which is just count and divide. Plus we said, account for the Dirichlet priors. Okay. So here, this is the same as fully observed map estimation. Okay, so this is Monte Carlo EM, and so standard EM, so I wrote this out in terms of one sample, z hat, right? Okay, but what we're really doing here is we're saying this is a Monte Carlo approximation to the desired distribution, right, which would be what we just wrote down in the previous slide, which is the posterior of theta and phi given just x, which sums over all possible z's for this thing. Whoops. So it would be a sum over all possible z's of p of theta and phi given x and z times the probability of z. Sorry. We'll just write this as, I'm going to write this in a slightly different way here. Probability of x given theta, so this is proportional to probability of x given theta, phi, and z, probability of z given just theta. Okay. So it's a particularly bad Monte Carlo approximation because we're only using one sample. Okay, a better approximation would be to approximate this by taking many samples z and averaging over them. Okay. Okay, so what about the Bayesian approach? So the Bayesian approach here would say we just want not a particular point estimate of theta and phi, which is what these EM algorithms are giving us. They're giving us back a particular value of theta and phi, just one. Bayesian inference says, let's estimate the whole distribution. Which is going to be p of theta and phi given x. Okay. And to figure out, what does that distribution actually look like? So this is a nice idea, but we're going to skip that. In general, this problem is intractable. Okay, so this is just a quick note about that intractability. So there was this paper by Sontag and Roy that partly addressed this. So exactly computing this posterior is intractable. And one way that we can actually think about this is that in order to do inference here, we would need to use something like the junction tree algorithm. Okay, junction tree algorithm, it's kind of closely related to the variable elimination algorithm that we talked about, but it does things a little bit different. So first, it moralizes the graph, which is going to convert the directed to an undirected graphical model. Second, it triangulates, which means that it, wherever there's a for cycle, which just means that you have some set of 4 variables like so, it triangulates by adding a new edge diagonally. Okay, and then it makes a new structure called a junction tree, where each clique in the original graph becomes a variable. Okay. And the time complexity is actually exponential in the size of those cliques. So for LDA, the cliques are going to be really large, at least sort of order number of topics. And so that means that the actual time complexity is order 2 to the number of topics. So if you have 100 topics, then we're talking the time complexity order 2 to the 100. Okay, so it turns out that further exact map inference in LDA is also NP hard for a large number of topics. Okay, so the point is that we can't just go straight in and do exact inference easily. Okay, so what else could we do? Well, one answer is we could just define an explicit Gibbs sampler. Okay, so what would an explicit Gibbs sampler look like? Well, an explicit Gibbs sampler for LDA, we'll sketch out real quick here. Okay. So an explicit Gibbs sampler for LDA would look something like this. So we would have basically to iterate through all of the different variables that we're concerned with, right? So based on this little plate diagram, we're going to have a for loop over the different phi parameters. We're going to have a for loop over the different theta parameters. And then we're going to have a for loop over the z's. So what this would look like is something like for k in 1 up to capital K, the number of topics. We could, for example, resample the vector phi k from the full conditional p of phi k given the Markov blanket of phi k. Okay, so let's actually just so that we have it handy, we can draw in the plate diagram here. This is theta n, z n n, and x n n. And then we have a block over here of topics, should have some prior data. So here, if we want to resample the phi k's, what's the actual Markov blanket for the full conditional? So what do we actually condition on here? So let's see, we need parents, children, and co-parents. So what are the parents? Just beta. Children? Uh-huh. So let's say all the x's, because any of them could potentially be using phi k, right? And all of the z's, since again, any of them could potentially be involved, and it's going to boil down to all of the z's that are currently assigned to topic k. Okay. So we only need tokens which are currently assigned to topic k. So there's a technical detail here, which is that formally, I mean, phi k does depend on all of the x's and all of the z's. It's just that because we know the actual structure of LDA, we know that only the ones that actually have the topic equal to that k are actually going to rely on it. Okay. So then we'd also have a loop for little m in the different documents 1 up to capital M. And we'd say for each, say, vector theta M, we could resample it from the full conditional that takes parents alpha, children z, and in this case, the co-parents are all of the thetas that are parents of the children of theta M. Okay, so this plate diagram, it's not always completely obvious what the co-parents are here. So let's actually jump to where we introduced this plate diagram notation. So last time we said, here's the example of a plate diagram for, oh, we didn't actually draw the explicit example, so I guess we need to redraw. Right, so if we had two separate documents here, then what's going on really is that alpha gives rise to theta 1 and theta 2. And all of the z's for theta 1 fall under just theta 1. And all of the z's for theta 2 fall just under theta 2. So there are no co-parents of the vector theta m. So in that case, we can just close the full conditional. And then finally, we have this inner loop, which says for each of the words, so n in 1 up to nm, we're going to resample zmn from the full conditional, which is probability of zmn given its parents, which is just the vector theta m, its which is all of the x's for document m, and its co-parents, which are all of the topic parameters, theta, or sorry, phi. And then lastly, the actual words are observed, so we're not actually resampling them. So this is the whole explicit give sampler. And the only remaining question is, what is the actual form of those full conditionals? So if we were to write those out, we would hope that the form of those full conditionals is sort of amenable to fast computation.
So in the first step, you said like phi k, each phi can depend on each xn. So aren't the phi other than k also be like co-parents of?
So aren't the other? Oh, yes, they are. And why? So you're absolutely right. So we should write this as all phi for not k. But I guess what will happen is the actual values, so what's going to happen is those phi not k terms are only going to actually affect all of the x's and z's that are assigned to topics other than k. And so when we're actually working with this full conditional, all of those terms will actually just drop out, and we won't need to actually compute them each time. So that's a great insight. Thanks for catching that mistake. Okay. Okay, so I'm not actually going to go into the details of these full conditionals because I want to now sort of just establish at a high level what this algorithm looks like. And now I want to talk about a slightly different version of a of a sampler called a collapsed Gibbs sampler. Okay. So essentially, what I want to make clear here is that I trust that you all could actually go in and figure out sort of the remaining probability / algebra required to articulate what those full conditionals are. Okay, so we're going to look at some full conditionals, but I want to do it for a slightly trickier setting. In this setting, we're only going to actually sample the z's, and because of Dirichlet multinomial conjugacy, which we saw last time, we're actually going to integrate over all possible values of theta and phi. Okay? So this is going to be what's called a collapsed Gibbs sampler, because we're essentially collapsing the values of theta and phi in a way that makes them sort of not show up explicitly in our Gibbs sampler. So the whole point is that here explicit refers to the parameters are explicitly sampled, and in the collapsed case we have that the parameters are not explicitly sampled. They're integrated out. Okay, or marginalized out. Okay. So what does this collapsed Gibbs sampler actually look like? Well, in some sense, the actual algorithm is sort of just a simpler version of what we just wrote down, which is that we're just going to loop over documents, words, and then resample topics only. So let's just briefly write that down for a contrast here. So the collapsed Gibbs sampler is going to look almost identical in that it'll have this resampling of the z's, but we're going to just drop the resampling of the phi's and thetas. So we'll say for each m, so for each document, and then for each word in each document, we're going to resample ZMN from a slightly different distribution, which is ZMN given only the x's. Oops. And also now the hyperparameters, alpha and beta. So before, we didn't have to include the hyperparameters in our full conditional, in the explicit sampler, because the parents were showing up for ZMN and the co-parents. But when we integrate over those, it's like we're marginalizing them completely out. So this probability distribution, what it is a marginal probability where we integrate over all possible values of theta and phi for the joint distribution of ZMN, theta, and phi given the Markov blanket, which is XM. Oh, sorry, I need to be careful here. So in our new version here, we should probably actually draw the thing so that don't leave this confused. So the mistake that I made here was copying down XM, when in fact we're going to look at all of the X's. Okay. So here, this joint distribution here is going to couple, because we're going to have the probability of ZMN phi theta times the probability of theta given alpha times the probability of phi given theta. Okay. So, and then this is integrating over theta and d phi. So effectively, what we're doing here is working with a slightly different model. And the different model we can express as a Bayesian network where we still have hyperparameters alpha, and we still have this notion of documents, but now alpha is sort of directly influencing the z's and the x's. And the x's are directly being influenced by the hyperparameters beta. So the whole trick here is going to come from the fact that we're able to tractably work with this model. So why is that possible? Okay. Oh, okay, so actually, sorry, before we get to why is that possible, let's say, why is this desirable? Okay, well, if we have a bunch of samples of just Z, then it turns out that we can get back a lot of the things that we might have wanted. So namely, we could estimate, say, the mean of the Z's, or we could estimate the mode of the Z's, or we could estimate a posterior distribution over the Z's. Or, crucially, we could get an estimate of the topic parameters and the document distribution, the document-specific distributions over topics. Okay? And how would we do that? Well, we would look at some count variables, which we'll define in a minute. That are just counts of the actual Z's. Okay, so this is where we're going. Okay, and here's the punchline, which is that the actual definition of the full conditionals for this collapsed Gibbs sampler works out to be incredibly simple. Okay, so it all fits on one slide. That's always a good first sign. And essentially, it's just count and divide. Okay, so let's first define our count variables. So NKT here is the number of times that topic K appears with word type T. Okay. So, for example, we might not know it yet, but maybe topic K is going to end up being something about hockey. And so the word P might be the word penguins. Okay? And so N sub hockey, comma, penguins is just the number of times that some ZMN equaled hockey and XMN equaled penguins. Okay, so what about NMK? So this is just the number of times that topic K appears in document M. So here this might be N sub hockey, comma, 37. And this would just be the number of times that Z sub 37, comma, N equals hockey. Okay. So the number of times that some word in that 37th document is equal to the hockey. Okay, in practice, of course, we don't have labels like hockey. Topics are just integers. There's some topic that's, topic 7. And maybe it will eventually look like a hockey topic, a distribution over hockey words, but we don't have that up front. Okay, so what is the form of the full conditional? Well, the full conditional is saying that the probability of some particular Zi, where here we're going to assume this sort of notation trick, which is that I is equal to some Mn pair. Okay. So why didn't we just write Z sub Mn? Well, there's already so much going on with sort of all of the different indices here that we want to just be able to talk about these count variables with and without the contribution of a particular Mn pair. Okay. So N sub kt minus I just equals the count without ZMN. And N sub mk minus I is just the count without ZMN. Okay. So it would be like if you were keeping track of these things globally, right? You could imagine like a little table representing NKT and MK. So how do you get NKT minus I efficiently? So if I give you NKT, how do you get NKT minus I efficiently? Okay, maybe if that's not obvious, let's do it as a quick example here. Okay, so efficient computation of count variables. So the first idea is globally store count variables nkt and nkm, or did I say nmk? mk, sorry. As tables. So as an example here, let's just look at nkt. So it would be a table, and the table might have rows for different k's. So maybe we have 3 topics, and it might have columns which correspond to the actual words. And we could say that the words are maybe things like aardvark and zebra. We just have 2 words in our vocabulary. So this is the actual NKT table. And the counts might be something like 7, 4, 2, 1, 6, 6. Okay. So given that, and further, let's go ahead and say that that these words, I mean, sure, they're things like aardvark and zebra, but they should also be indexed by numbers or something. So let's just say our words are represented by these letters, A and Z. So given that n sub 2z is equal to, So given that the actual z value for one of our documents is z11, so that's the first word in the first document, is equal to, not aardvark, but topic 2. And x11 is equal to word A for aardvark. Okay. What is n sub kt minus I? Right, so we just want a new table here. That leaves out for I equals 1, 1.
So do we just put a 0 there?
So I guess the question is, yeah, like what would be 0?
Like, how do you leave it out?
So we're just leaving out one of the words. So this is the global counts, right, for all words in all documents, right? 4 times the topic 2 is associated with the word aardvark. 6 times the topic 2 is associated with zebra. 7 times the topic 1 is associated with aardvark. And so if we're leaving out just the particular I equals 1, 1, then what's the remaining counts?
So what's observed here, given that?
So what I'm trying to say is that this is observed, the actual count table for globally for the whole corpus. And I'm just telling you one of the word topic pairs. And now I'm asking you to leave that pair out. Okay, so is the first table entry affected by leaving that out? Or is it still 7? If we leave out the occurrence of aardvark with topic number 2, is the number of times that topic number 1 appears with aardvark going to change? No, it should be exactly the same. So this should be 7. Okay. Same thing goes for topic 1 assigned to zebra. There's still going to be some other word somewhere in the corpus that's still assigned to, that is word zebra assigned to topic 1. Okay, so here we had 4 cases where aardvark, the word aardvark, is assigned to topic 2. And now I'm leaving one of them out. So what's the new count value in that cell? 3. And then all the other cells stay the same. So the point is, if you have the full NKT table, computing the NKT minus I table is just a matter of subtracting away one of the numbers. It's decrementing it by 1. Okay, so now let's look back at the full conditional. So the full conditional is using that subtracted away version of the table, and all it's saying is take the number of times that topic, and so let's be a little more specific here. So I is equal to mn, and t is equal to xmn. Okay, so in the numerator of our full conditional, take the number of times that whatever the actual word that we're concerned with was assigned to topic k, and add to it beta t, which is just coming from the Dirichlet prior. And then divide by summing over all of the counts for all of the different topics. And then in the second term, we're just saying count up the number of times that this particular topic appeared in the current document M. Add in our Dirichlet prior count alpha k, and then divide to get something normalized. Okay. So why does this work? So this full conditional is actually maybe a little more interesting than those count variables let on. So what's actually going on here is we're saying this conditional probability is the probability of all of the x's and all of the z's divided by all of the x's and all but one of the z's. Right? This is just a definition of conditional probability. We're just conditioning on everything except for the one zi that we care about. Okay? So because the denominator doesn't depend on zi, we can just drop it and say, well, this thing is proportional to p of x and z, the joint distribution of the words and the topics. Okay, so according to LDA, we have some Bayes net, and it has some independence assumptions. And so that joint distribution of x's and z's decomposes into p of x given z and beta and p of z given alpha. Right? We can see that by jumping back to this red Bayesian network and just decomposing the probability in that way. Okay, but now we need to remember where that red picture came from. The red picture came from the original model that had the phi and the theta parameters. Okay. So here, we're actually going to bring back the phi and theta parameters. Those integrals that we had integrated out, they're actually still there. Just because we integrated them out doesn't mean they're sort of gone. It's just that they don't show up if you are marginalizing them. So bringing them back into the fold, we now get this expanded version of the joint likelihood. And you'll notice that I was able to essentially take the integrals and separate them out because the integration here is associative. So phi doesn't appear anywhere in these latter two terms, and theta doesn't appear anywhere in these former two terms. And so we can associate the integrals in that way. Okay. And the interesting step is that we can jump from these integrals to these beta functions. Okay? And then jump from the beta functions to the counts. So the question is, how do we actually make this leap? Okay, so this now comes back to Dirichlet multinomial conjugacy, which we saw last time for the naive Bayes example. Okay, so what we said last time was that if we have a Dirichlet multinomial model, right, like something like this, where we say draw a distribution over words, like a topic distribution, and then draw a bunch of words from that topic distribution, that the posterior over phi actually has the form of a Dirichlet based on beta and some count variables. Okay. So if we take just one of those two terms that we were looking at, okay, let's jump back here. So let's look just at this term. Right? It's P of z given theta, P of theta given alpha, integrating over theta, where P of theta given alpha is a Dirichlet and P of z given theta is a multinomial. Okay. This is just another example of that. I guess I have a change of parameter names here, but it's again just a multinomial and a Dirichlet. So what do we get? Well, substituting in the multinomial, we get this product of a bunch of multinomial parameters times the PDF of the Dirichlet. Where here, b is just this beta function. And then what we can do is the beta function only depends on alpha, so we can move it outside of the integral. Okay. And we can take these two exponents and combine them together. Okay. So once we've done this, now we can say multiply by 1, right? This is just the number 1, represented in a funny way. Okay. So that's all I did was just multiply by 1. And then I can move one of the numerator of that 1 outside the integral. Okay, so we take this and move it outside, and that gives us the next line. And the beautiful part here is that this is a Dirichlet distribution. Right? Specifically, it's a Dirichlet of a count vector n and some hyperparameters alpha. In fact, this is exactly the posterior of the parameters. When we integrate over those parameters for some posterior, this whole term just goes to 1. And we're left with this ratio of beta functions. Okay, so there's just a little more algebra to go from beta function to count variable, so we'll skip that step. But basically, we're just doing that twice, right? There's a Dirichlet multinomial distribution here, a Dirichlet multinomial distribution there. Both of them have corresponding counts over topics and over documents. we do that trick of integration to get back the ratio of the betas, and then we can simplify that ratio of beta functions to be just these counts. Okay. So the whole collapsed Gibbs sampler is really working with this sort of simplified Bayesian network where those are integrated out. And so the remaining question is just how do you actually implement this thing? And essentially what you do is you work through everything, and initially you sample some assignments to the topics that are just completely random. Okay? So these are completely random initialization of topic assignments. Okay, and then of course whatever ZMN works out to be is going to be some value k, and so you should just increment all of your global document topic counts, document topic sums, and topic term counts. Okay. So this nk is just going to sum over all the possible t's, and this nm is going to sum over all of the possible k's. Okay. So now, here's the actual Gibbs sampling algorithm. So you're going to pick a particular word, one of your ZMN variables, and you're going to decrement the corresponding count variables, NMK and NKT, and then we've added these additional convenience variables, NM and NK, that are just the full count for all of the words in document N and all of the words assigned to topic K. Okay, and then all we need to do is sample the topic K using those counts, and then re-increment the corresponding counts using the new K tilde that we just sampled.
Why are we decrementing the word space?
Oh, so why? Yeah, great question. So let's go back to the full conditional here. So the full conditional is the probability of Zi taking on some new value k, and it's conditioned on all of the current values for Z, except for that particular word that we're currently looking at. So if we look at these full conditionals, right, in order to get the actual probability right, we need to leave out whatever the current assignment of Zi is. Right? So if you think about this from just sort of a general Gibbs sampling perspective, what we say would be something like, in a general Gibbs sampling setting, right, the full conditional of some, P of A given, say, B, C, D, and E is going to be something like, here's A, and it might have parent B, and child C, and D, and co-parent E. So that probability depends on B, C, D, and E, right? But generally what we're concerned with is, the probability of A taking on some specific value. Like, so we would say, we want P of A equals K given B, C, D, and E. And to compute that, we need to know what the specific current, rather than K, let's say little a. But we can't just work in abstract. We need to talk about some specific probability of A equals a specific little a, given that B equals a specific little b, and C equals a specific little c, and D equals a specific d, and E equals a specific e. Okay. And so the point is that in order to actually draw this sample, what we need to do is compute the probability of zi equaling each of the possible different topics. Right? We need to compute that full distribution over topics for all of the different values that zi could take on. And then we sample from that distribution. So that's why we're leaving out the former assignment k, and then once we have the new k tilde, adding it back in. Okay. So there's this last detail of how do we actually recover the actual parameters, and so here this is kind of interesting. So we can recover parameter expectations, and we do so by observing that the probability of a particular theta m given all of the x and z values and alpha is equal to a Dirichlet over vectors theta m conditioned on parameters nm plus alpha. And similarly, the posterior over phi k, that vector, again conditioned on all of the x's and z's and beta, is a Dirichlet over, phi k, given the count vector nk plus beta. And so what we typically do then is we say that the expected value of the vector theta m under that Dirichlet distribution is obtained just by looking up the expected value of a Dirichlet. Right, so if we went to Wikipedia right now and we looked up what is the expectation of a Dirichlet distribution, it would just be the following. So for a Dirichlet with parameters alpha, or rather, let's say for a Dirichlet over vector theta given parameters alpha, we have that the expected value of theta is just the, sorry, let me be careful here. So if we take this expectation and then we select the kth entry, that's going to be alpha k divided by a sum from j equals 1 to k of all of the other alpha j's. And so what we can do up here is just take the expected value of these parameters, which is just going to rely on these count variables. So it'll just be that the let me make sure this is specific to one parameter. So we could say if what we want back is some specific theta mk, then we're going to define it to be, this will be our expected value, the kth entry of this expectation. And that's just going to be the count of NMK alpha divided by summing from j equals 1 to k over nmj plus k. And similarly then, phi kt, we would just define as the expected value over the phi vector, looking at the tth entry in it, and that's just going to be nkt plus beta divided by a sum over, say, all the different possible word types, nks plus beta. Yeah.
Should the alpha and betas have, when this is still like k and t, are they vectors?
Oh, sorry, yeah. So here I'm being kind of ambiguous about it. There's two ways that we could do this. One is we could say that I'm cheating and I'm using sort of NumPy broadcasting. So when I write alpha here, it's actually a scalar, but you're going to add it to each of the entries in the vector. Okay. The other thing is we could just say that here we have vector alpha, and vector alpha is defined so that its kth entry is just equal to alpha, and similarly for vector beta. Yeah. Okay, so the key takeaway here is that this bit is Bayesian inference, and then this is actually obtaining a point estimate of the parameters. So in the end, maybe we actually do get back a specific value of the parameters so that we can inspect it. But ultimately, we've actually succeeded in doing Bayesian inference. We actually can perfectly express what the distribution over the parameters is for a particular training set. Okay. So next time, we'll wrap up with a very brief look at a bunch of different extensions to this model, and we'll move on to talking about variational inference.